Okay, now we're still looking at the electric field from the line charge, and let's see what we need to do in order to put everything together. We're going to put our RSP value, the unit vector, right here, and we're going to put this magnitude term right down there. Now those are very well defined. Let's see what dl is. Okay, our little unit dq was this little piece of charge, which is rho L times dl. In this case, we can just observe that dl is dy. The other way that we could do it is we could look to see what doesn't change. dx doesn't change, dy doesn't change, dy changes and dz does not change. If you look in table 3-1, you'll find an equation for dl. It's in vector form. In the x direction, it has dx. In the y direction, it has dy. And in the z direction, it has dz. That's what you'll find in table 3-1. We're not going to use the vectors in any of these in this example, but we have to decide if it's going to be a dx term, a dy term, or a dz term. dx does not change, it is 0. dz does not change, it is 0. The only part that we are left with is dy. Now this may look like a very messy equation, and in fact it is. Most of the time, if you are doing a realistic electromagnetic simulation, it is even much more complicated than this. This wire is not likely to be straight. It's likely to be a series of wires, or flat or twisted, or mixed up with plates and wires in very complicated ways. Almost always, if you want to really be able to solve these problems, you are not going to be able to do the integral analytically, and that's okay. There are good numerical ways of solving the integral equation, and I'm going to give you a reference to that on the website so that you can go and find ways that we use numerical integration to be able to solve these problems. So bear in mind the steps that we have done are exactly the same steps that I described at the beginning of this lecture. We create a coordinate system and define an origin. Our origin was right here. We define rs, the vector between the origin and our source. We define our p, the vector between the origin and the point of interest, and then we subtract those two in order to find a vector from the source to the point where we want to find the electric field. We find the unit vector of the RSP and its magnitude in order to use them in Coulomb's law. Now we can see here that we have a line charge. The dq for a line charge is always going to be rho L dl. dq is always rho L dl for a line charge. Then, in order to find the electric field, we simply integrate, and in this case, we integrate over a line because it's a line charge. We integrate from ys equals 0 to 3, and we've just plugged everything in and we do this integration. Now let's examine one other question. What if, instead of just finding the electric field at the point 4, 3, suppose that I wanted to find the electric field at other locations up and down this axis, where instead of finding it at 4, 3, I might find it at 4y. Now I'm going to do myself a favor, and I'm going to write yp here because I mean that the point where I'm finding the electric field is varying. That is different than ys because that is the point where the source is varying. In that case, instead of 3, this would be yp. And so on. When I did my integration, this dy term, is that integrating my ys or is that integrating my yp? Because what I'm integrating is adding up sources, my derivative term is always related to my ys term. It is not related to my yp term. My yp, for all intents and purposes, is treated as a constant value, even though it is a vector. You do not integrate it. You simply leave it in the equation and bring it out, and then you would have the electric field as a function of yp.